Joe, you got the CPU running yesterday?
Yeah.
I after watching a couple of people playing with the CPU, I decided to put up 2 zipped projects, which I hadn't done. Not because I was being mean, just because I hadn't gotten around to it. But I got around to it yesterday. So both the serial CPU project and the video CPU project now have a zipped file associated with them, which you can unzip, and it should compile and run as is. Includes the MIF file and all of the pieces. So again, any questions about Lab 2? This so-called direct form type 2 which I was talking about last time, is nice and compact to sum up on a stack machine, because you're doing a very long sum and difference, and so you can issue in a stack language, you can issue commands like b1 xn add b2 xn minus 1 add multiply b3 x n minus 2 add multiply, and the appropriate result is always on the stack. So here we're taking the first 2 operands by using their name. By using their name, they are pushed onto the stack. The add operator then adds them and leaves the sum on the stack. We then push 2 more values onto the stack, so the stack now has 3 values on it. We add the top 2. Now there's 2 values on the stack, except I've got it backwards here because I'm an idiot. And that's why people were, multiply, add. Then you multiply these 2, and so there's now, let me start over. I push these 2 onto the stack, there's 2 values on. I multiply, there's now 1 value. I push 2 more values on, there's now 3. I multiply, takes these 2 off and replaces it with the product on the top, and there's still 1 on, so I now add. Now I'm down to 1. I push 2 more on. I multiply. I add. I'm down to 1. So by doing a series of operations like this, I can use the stack as a multi-register summer and evaluate this sum of products, which is what you're going to need to do in the program that you write. Any questions about Lab 2? Any problem with the compiler? I expect to see some problems this afternoon. Okay, so if there's no questions about Lab 2, I'm not going to say anything more about Lab 2. I'm going to talk a little bit about hardware filtering, which you're not going to do for this lab, but which you may want to do later in the semester. We'll talk a little bit about hardware filtering, parallel hardware, and then we're going to start talking about Lab 3, because Lab 3 is big and complicated. Lab 2 is fairly straightforward. So another way of implementing this infinite impulse or this filter structure is to pipeline the inputs and the outputs so that we can do a whole bunch of adds and multiplies on every cycle, and so we can speed up the computation of the filter quite considerably. In fact, on this architecture, we could easily expect to be able to build an infinite impulse response filter that produces a new, say, 10-bit or 18-bit sample at 100 megahertz. You're not going to do that with a software version. For the software version you're doing for Lab 2, you only have to put out a new result 44,000 times a second. And so it's easy to do that in software running on the CPU that you build. But if you wanted to do a high-speed filter, for instance, software radio requires high-speed filters. If you were to do head reference transfer function, then you would require some high-speed FIR filters. Head-related transfer function would be taking a source of sound and doing the appropriate filtering so that it sounds like it's coming from a place in space. So you can move the apparent source around your head by doing the appropriate FIR filters. It turns out that you need to do about 428 tap FIR filters at 44 kilohertz, and so you need to do a little bit better than a software filter. But let's talk about a basic parallel hardware structure that you might build to implement a fast filter. I'm going to represent a multiply by just a symbol like this. So I'm taking xn, the nth sample, the current sample, multiplying it by b1. And we're going to add this, but it's kind of a trivial add because there's no other operator. There's we're going to feed xn into a register, full width register, sometimes referred to as a z-1. The output of this register is going to be multiplied by B2 and then added to the output of this multiply. We're then going to add another pipeline register whose output will be multiplied by B3. Added to the output, and so on. But let's say we have a 3-tap register, 3-tap filter here. The output is going to be yn, but we need to feed this back through a delay. A register, which is then going to be multiplied by minus A2 and added in, followed by a register minus A3 and added in, and so on. So every sample that gets clocked in is going to have an output clocked out, and all of these multiplies happen in parallel, so to speak. But there's a real basic problem with this parallel implementation that limits the clock frequency at which you can run it. And what is that? The multiplication and the addition have to happen on the same cycle. That is correct, and that does slow it down. So that's one aspect of this which makes it slow. There's another aspect which is bad also. Say again? Data, you mean across here or through here?
Through the next step.
Through this step. Yes, it's got very bad add depth. So this add can't occur until this one occurs. This one can't occur until this one occurs, and none of them can occur until before the multiply occurs. And so the depth, the multiply add plus the depth of the adds limits the rate at which you can clock this particular filter topology. And so it's possible to rearrange. This is a very naive kind of implementation, and it's really based upon looking at the structure of the direct form type 2 and saying, well, all I have to do is shift. This is the input. This is x of n minus 1. This is x of n minus 2, and so on. But we can change this around to make a much better structure. Same input. But now we're going to multiply this by B3. Add it. And register it. Take the output of this, multiply it by B2, add it, register this, take the output, multiply by B1, add it, and the output of this will be yn, which is then fed back with coefficients minus A2 and minus A3. It's a little harder to figure out the causality of this, but if this is the output, then this one must be the sample before, and this is the sample before that. So going to this structure does a couple of nice things. One is it limits the add depth to one operation, or maybe two operations depending on how you think of it, per pipeline step. And so, but you still have to do the multiply in the same cycle as the add, and it halves the number of registers necessary. Halves the number of pipeline registers necessary to implement this. Yeah.
B1 becomes the multiplier for xn minus 2, and B3 becomes it progresses in this direction.
Wait, I'm sorry, say again, please. B1 is multiplied by xn and then goes directly to the output. Right, and then, yeah, it's, so So this is a much, much better structure, and this is what you should implement in hardware if you want to do a second order filter. So, but there's still a better structure we can build if we're going to do more than second order filters. The basic problem is that if you can be shown by doing an operation like this. We define a Butterworth filter with 2 taps and a cutoff frequency of 0.1 normalized to the Nyquist frequency. And we find that the B vector is given by 0.0201, 0.0402, 0.0201, and A has values of 1, minus 1.56, and 0.641 something. So the dynamic range of the coefficients then is about 100 to 1. This one is about 1/100th the size of this. Not quite, but 1/80th or so. And so we have to be really careful with this kind of, if we just plugged in the B's here and the A's here, we would have to be very careful about the number of bits we maintain, because an 80 to 1 or 100 to 1 coefficient range means that they differ in size by 7 bits almost. So that if you're only maintaining a 10.8 filter, then and you call the fractional size 0.02, then you only have 1 or 2 bits of accuracy left here to represent the 0.02. If we go to a filter which is of size 4, and in Matlab you can try this with butter for 0.1, then we get coefficients that are like this: 0.0004, 0.0017, 0.0025, 0.0017, 0.0004, and A is equal to 1 minus 3.1, 3.1 minus 2.1, and 0.43, 0.44. So now the dynamic range is 1,000 to 1. Now 16 bits will barely do it. Well, 12 bits will barely do it. 16 bits you're still okay. But so you could ask yourself, is there a way of setting up the filter that doesn't require as many significant bits in the coefficients? Is there a way that we can somehow take these high order filters, 4 or 6 or 8, and factor them in such a way as to minimize the dynamic range of the filter coefficients? And it turns out there is. And so what we're going to do is rewrite, we're going to factor the filter into second order sections. So-called SOS. We're going to filter them into separate them into second order sections. And without going through all of the horrible mathematical details of taking a transfer function and factoring it, which probably some of you did in complex variables someplace, or maybe in a linear systems theory class, we're just going to use the nice MATLAB function, transfer function to SOS, and you feed it a vector of B's and a vector of A's, and it calculates two structures for you. It calculates a matrix of second-order sections, and it calculates a gain that has to be multiplied by the result of the second-order sections. So the SOS structure is a matrix of B0, 1, B11, B12, yes, 1, 1, 2, 1, 1, A11, A21. The next row is B02, B12, B22, 1A, 12, A22, and so on. So every row of this constitutes a new filter. And the new filter is of the form one, the gain being 1, that's an easy multiply. 2, that's an easy multiply. 1, again. I better put some registers in here. Minus A1K and minus A2K. And if we were to carry this out for the filter we just did with butter for 0.1, we would find that this structure has value 1, 2, 1, hence the 1, 2, 1 here. 1 minus 1.47.555, and the second row is going to be 1, 2, 1, 1 minus 1.7.78. That's cool, because now the dynamic range of coefficients here is more like 4 to 1. So it reduces the number of bits we have to carry to get good accuracy. But what's G? G is equal to 4.16 times 10 to the minus 4. Oh, man. So if we just multiplied by that, we'd lose, again, about 12 bits of accuracy, maybe a little bit more. So we have to be a little clever and do something like this. We have some xn coming in, multiplied by the, let's say, the cube root of g, then into section 1, SOS1, then multiplied by the cube root of G, into second order section 2, and then cube root of G. So hopefully by breaking up G into its cube root, gives us, at the cost of an extra multiply, we can not lose too many bits of precision before we do the arithmetic. I have to tell you though, second order section arithmetic works best in floating point, because now multiplying by a constant costs you nothing in terms of accuracy, because all of the accuracy you lose in a floating point operation comes in the subtracts, right? Subtraction of numbers that are almost identical. And we've optimized that by making all of these numbers about the same size. So second order sections work best if you have floating point arithmetic available. There are no floats in Verilog, but there are now 3 different versions of floating point hardware that you can easily implement on this FPGA in Quartus 2. The first is full IEEE floating point 24-bit mantissa 8-bit exponent, which is supplied by Altera and is available in the Mega Manager. You can implement about 1 second order section on this chip before you run out of hardware if you use IEEE floating point, because it's monstrous, right? You might be able to do 2 second order sections. So IEEE floating point is really nice because you don't have to think too much. It's so accurate that it always works, unless you're designing atom bombs or something that requires very highly iterative, high precision solutions of large differential equation nets. Then it usually works, but sometimes doesn't. But it's way accurate, way too accurate for what you need for digital filtering. You can show that for doing, say, an MPEG encoder, an MP4 encoder, you only need about 9 bits of mantissa. You don't need 24 bits of mantissa. So I implemented a 9-bit floating point, and one of the students last year to do Lab 4 implemented 18-bit floating point. So there's 9-bit, 18-bit, and 32-bit floating point available. You can implement about 70 multipliers in 9-bit and about 35 floating point multipliers in 18-bit floating point. So if you were going to do second order sections in hardware, it would probably be best to do them in 18-bit floating point. For this lab, you're not using hardware. You're using software running on a CPU. And I'm only asking you to implement second order filters, and so there's no particular reason to use a second order section. Any questions? There are some really nice design application notes from Altera. So if you Google up Altera application note DSP or finite impulse response filter or infinite impulse response filter, you will get a fire hose worth of information. And I'll talk more about filtering in 3 or 4 weeks after we get through the kind of specific stuff we need for each lab. Towards the end of the semester, we'll take requests for what you'd like to hear about. So start thinking. In the past, people have asked for lectures on adaptable computing, whatever that means, where you can change the structure of the hardware in real time during a problem solution. That means many things to many people. People have wanted to hear about parallelizing computer graphics, head-related transfer functions, dynamic noise cancellation. Think about what you'd like to hear about later on in the semester. I'll certainly talk more about digital filtering if you want. Any questions on Lab 2? Don't be shy. So either that means, the fact that there's no questions means A, it's really easy, or B, nobody started on it. In which case you're going to be really busy this week. So let's start talking about Lab 3. I'll be happy to answer questions, but if there's no questions, we're going to go on. So Lab 3 is going to ask you to generate a very large parallel computer. And it can be large in this, it's going to be large in the sense that we're going to ask you to take a two-dimensional array of nodes, and treat this two-dimensional array as if they're locations on a square drum head. Square, most drum heads are round, but there's no reason why you can't build a square drum head. Treat them as if they're locations on a square drum head. Add some energy to the system. In other words, hit the drum head, probably near the center, but that could be a parameter you choose in your simulation. And then have the FPGA calculate the shape of the drum fast enough that you can listen to the result directly. So you press a button on the DE2 and the thing is going to go boom. Right? You're going to hear it directly. So it has to be calculated at real-time rate. It has to be calculated at 48,000 samples per second, or some multiple or some submultiple of that. I don't care whether you compute it at 16,000 times a second or 48,000 times a second or whatever you want, but you are going to be partly graded on the product of the sample rate times the number of nodes. So you can trade this off. If you want to do lots of nodes, you can lower the sample rate. If you want to raise the sample rate, you don't have to do as many nodes. I thought I was doing pretty good when I got 100 or 150 nodes running at 48 kilohertz. I figured that was good. 10 by 10 grid was, all right. A student 2 years ago came up with a solution, 10,000 nodes running at 48 kilohertz. Beat me by a factor of 100. That's why this class is so much fun. You never know what kind of weird stuff you're going to see. So, you have to think a lot about how to optimize this design. You have to calculate a bunch of nodes. I'm not going to specify how. You have to figure that out. I mean, well, we'll talk a lot about different ideas about how to do it. You could build 4 big honkin' processors, divide the grid into 4 pieces, compute each of these grids on separate nodes, on separate CPUs. Why does this work? It works because you don't need to pass information back and forth between CPUs except at the boundaries between the 4 regions. And as the grid grows in size, the amount of computation internal to the quarter of the grid grows as grid size squared, whereas the communication only grows as the grid size to the first power. And as you probably all know, communication between processors is relatively slow compared to arithmetic within processors. And so you want to be able to do a lot of calculation on each node and minimal communication between nodes. So you could divide this into quarters this way. You could divide into quarters this way. You could stripe it. You could, instead of building 4 CPUs, you could build a little tiny CPU for each node. In other words, you could build a state machine for each node that always executes the same 10 instructions, the same 10 arithmetic operations, 10 or so. We'll talk about what those are fairly soon. The same 10 or so arithmetic operations, and there's no conditionals here, there's no branching, there are no loops at all except to compute and compute and compute the same thing over and over. So all of the state machines will stay in phase. There's no branching, they all execute the same code. You can clock them all off the same clock with the same state clock, and they will all stay in phase. So you could build n² state machines. Cooper.
Does that have to be square?
Does it have to be square? No, it doesn't have to be square even. Some models are better. Drums tend to be round or roundish, although some drums are elliptical. But if you wanted to model a thin plate like this, then, and you hit it someplace down here, you might get something more gong-like or chime-like than drum-like. There's another thing we have to talk about, though, for drum-like versus chime-like, and that is that drums typically have their edges pinned down on a frame. What's that called? If u equals 0 on the edge, u now is the vertical displacement. If u is the vertical displacement and u is equal to 0 on the edge, then that's referred to as a... Does anybody remember what that boundary condition is called in a partial differential equation? Is it called a Dirichlet condition? D-I-R-I-C... Boy, can I spell Dirichlet? D-I-R-I-C-L-E-T, right? Isn't that how it's... H? H-E-T? H-L-E-T. Thank you. H-L-E-T. Dirichlet condition. So, but if you just take a piece of steel and hang it in the air and smack it like a gong or like a chime, then the edges are free to vibrate. The edges vibrate, but no energy can pass by the edge. And so the derivative, the slope has to be 0 at the edge because there's no restraining force on the edge. Steel being much stiffer than air. And so we have the condition that du the direction perpendicular to the edge has got to equal 0. And that's called a what kind of condition? That's a Neumann boundary. Von Neumann boundary condition. You get different harmonic structure. If the edges are free to vibrate, you get a different harmonic structure than if the edges are pinned down. It sounds different. You can implement all of them if you want. You could choose M, you could choose N, and you could choose the boundary conditions as either free or fixed. But the product of Fs times M times N is going to be one aspect of the grading. The boundary conditions actually don't cost you too much, so that's almost irrelevant. We'll talk in some detail about that. So, the first design decision is, are we going to go lots of lightweight processors, so-called single instruction, multiple data, SIMD supercomputer, SIMD computer, single instruction, multiple data, or are we going to do a heavyweight processor with just a few of them? You have to do one or the other because you're limited to a total number of logic elements on the chip. And I don't know what the best solution is. It depends on how you implement it. And so you're going to have to choose one and go with it. And partly it is determined by, do you like software better than hardware? If you like software better than hardware, maybe writing a processor that executes quickly is better than building a lot of little state machines. On the other hand, then you have to deal with the complexities of communication across these interfaces. Whereas if you build a little tiny state machine, then every node just has 4 nearest neighbors, and you connect them up neighbor-wise. Every node has exactly the same configuration as every other node, and so you just duplicate them. It's a hard choice. I strongly suggest that you read the theoretical papers that are attached to Lab 3, maybe starting now. It's only a week until Lab 3. The nice thing about starting early is it gives some coprocessor in your brain a chance to think about it when you're thinking about something else. And you do have all these weird coprocessors that operate outside your control. I've quite often had the experience of working hard on a problem, not knowing the answer, going to bed, getting up in the morning and knowing the answer. You know, I'm brushing my teeth and oh, I know the answer to that now. Something worked on it while I was asleep. Right? Some chunk of me worked on it while I was asleep. And you've probably all had this experience of working hard. You have to set up the problem for the unconscious piece of your brain. You work hard at it, you think a lot about it, and then you go off and do something else. Play racquetball, walk down the street, eat dinner, and you just suddenly know the answer. But you can't do that unless you work hard at setting it up. So you may as well spend an hour or two thinking about it early so that you can let this unconscious coprocessor work in parallel while you're sweating away on Lab 2. So what we're going to have to do here for the next lecture or two is to is to talk a lot about these differential equations that describe the wave equation on a thin plate. Talk a lot about the differential equations, how to discretize the differential equations into a difference equation so we can solve them on the computer, on some sort of computer that you're going to build. And then talk about the hardware optimizations that are implied by the discretized differential equation, and how you're going to go about implementing that. Is it going to be fixed point or floating point? Is it going to be fine-grained or coarse-grained? Is it going to be shared memory? Is it going to be message passing? All these things that you're going to have to decide upon really before you start coding it up. Is it going to be semi-serial? After all, if a single node only takes a few cycles to, say, 10 arithmetic operations, is it possible to share nodes in time in some clever way so that you can simulate a small region or do a small region in parallel and then duplicate that in series over each audio cycle? There's lots of interesting trade-offs here. Makes it a good lab because there's no one way to do it. Any questions on this? Another thing you may want to do is to play with the Matlab code that's in the lab write-up, because it will make sounds, but it doesn't do it in real time. It takes about a second to calculate, it takes 2 or 3 seconds to calculate a second's worth of sound, at least on my desk machine. You may also want to listen to some of the examples from the last couple of years. The students have recorded WAV files off the FPGA so you can, for your listening pleasure. Anything else? I'll see you in lab in about an hour.